first, this is just like a little example of packages that are already written, stuff that people have already written that's already out there you can download to do things you might want to do in the robot world. There's motion planning packages, there's SLAM, there's dynamic modeling, human-computer interaction, blah, blah, blah. The one I want to mention, too, that's really cool is this image processing one on the very bottom. OpenCV, I know a couple people in here have used it. A couple years ago, Willow Labs, I don't know if they took over OpenCV or made a deal with the guy that was developing it, but they are now like, they are OpenCV. They own it, they do all the development. When you install ROS, you get OpenCV, and if you were to write an OpenCV piece of code that did some sort of image processing, they provide a functionality that just allows you to take a camera stream or a single image and just pass it to that already existing OpenCV node. It will do the processing and return. So any sort of image processing you could possibly want to do is very easy to integrate with ROS. This picture on the bottom right is me, and that guy is David Liu. He's a PhD student in computer science at University of Washington, St. Louis. And that's like a standard OpenCV demo that finds people's faces in an image. But we were using it with ROS, and I saw the code. It was only a couple of lines. And the only reason I mention it is because, just by sheer coincidence, he's in Chicago on Friday, and he's coming to visit me here, and he's like one of the developers of this stuff. He's published a ton of ROS nodes. So if you guys have any questions that like Jake and I have no clue how to answer, he'll be here on Friday for most of the day, and so he can answer a bunch of that. So the first example I want to talk about is the PR2. We've already mentioned it a bunch of times, and it's sort of like the most complicated, most ROS integrated robot out there. It's super expensive. It's got all kinds of computers on it. It's got 2 computers on board, both running ROS. There's usually sets of master computers externally also running ROS. They're all communicating simultaneously over Ethernet, passing huge volumes of data. Look at the hard drive. Each computer on board has 2 terabytes. You have 4 terabytes on board on just the robot that is being filled up. And so yeah, this thing is obviously designed to work with ROS. It's sort of the most ROS integrated, most complex thing. Has anyone seen videos of the PR2 before? Okay, well then we have to watch this video. So here's the PR2. The guy that's talking, narrating it, actually Jake went to high school with, which is kind of funny. But
Hi, I'm a member of the Willow Garage Pool Shark team, and we just programmed the PR2 to play pool. At Willow Garage, we like to challenge our ROS software by doing short hackathon sprints. These sprints help spark new ideas, test our ROS software, and most importantly, are fun. Our most recent sprint was a game of pool with the PR2. This required tackling several different problems at once. In order to get the PR2 to use a pool stick, we built a special grip and bridge so that the PR2 could use its wrist to power the stick. 2 other challenges were finding the ball and localizing the table. To find the balls, we used the high-resolution camera with a color blob tracker, as well as a casino set of billiard balls that were easier to track. To locate the table, we used corner detectors to find the diamonds on the edge of the table and used the bottom laser sensor with AMCL to detect the legs of the table. Once the PR2 knew where the balls and table were, we could pass that information to our shot planner. We used FastPhys, open-source pool physics library by Alon Altman, to check the results of our planned shots before executing them. We began our pool playing sprint on Monday morning. By Friday afternoon, the PR2 was successfully pocketing shots. It even surprised us by making some fairly long shots, as well as shots from difficult angles. While there's definitely more to improve, our team is excited to see how much can be accomplished in just 1 week. All our code is available on ros.org in the billiard stack.
So I want to point out that they used somebody else's code to get that running.
the motion planning library, the thing I'm going to talk about next,
Yeah.
is what they used for determining what to make that PR2 do. So if you had $400,000 and bought one, you could run that right now. Just install and build, and you could do that. So on the exact opposite end of the spectrum is there's not even a robot involved in this ROS package. Kavraki Lab at Rice developed this piece of software called the Open Motion Planning Library. It's basically just a huge collection of motion planning algorithms. And it's got like a C++ front end. It totally wasn't related to ROS. They developed the whole thing, and then they're like, wow, everyone's using ROS. Let's turn it into ROS. And then they just basically wrote a ROS wrapper around all this pre-existing code. And now that's a ROS package that people use like crazy for motion planning. So that's like sort of the opposite. There's no robots or anything involved. It's just a piece of code. Somewhere in between is this robot called the ReZero. I chose this one because it's a ball bot, like Eric worked on, that was developed at ETH in Zurich. And essentially, you've got a ball, it's got Omni wheels driving it, and they have a computer on board that is running ROS, and microcontrollers running the motors. Those microcontrollers are interfacing with ROS on the small PC that's on board. I mean, it's a tiny PC, it's like this big. And then they have another computer running ROS, and they're doing all the like overall control of this thing, like telling it where to drive and stuff, via a separate computer over a ROS port. They actually controlled it all with a website. There was an HTML page, and you would like drop down menus like drive forward, and it would start driving forward. And ROS, like that's something that's really hard to do. But ROS just, I was like, wow, you guys must have programmed a ton. And I met these guys, and they're like, no, ROS just sort of handled all of it. So there's another one where ROS is being run on board, but it's not nearly as advanced as the PR2. I got a little video of it running. It's really short. It's all fine. It has a LiDAR sensor. It's actually following these things. It's finding them and following them. So the next example, yeah.
You guys at some point talk about the minimum specifications for the operating system?
So on the computer, they're not ridiculous. You can never run it on a PIC. But on a computer, pretty much any modern computer can run it. I don't know them off the top of my head.
Okay.
It takes about 1 gigabyte of hard drive space.
Okay.
Just big, but it's not ridiculous.
I think the real hindrance, if any, would be if you're trying to do visualization. Like my laptop can't run. It can run ROS fine, but as soon as I start trying to view all this 3D data coming in from the Kinect, it just bogs. Can't do it.
Okay.
But that's a graphics problem.
So the final example that I'm going to talk about is sort of, this one's the most important, because it's how I think most of the projects in this lab would probably end up working. This is the quad rotors at Penn. They were in the video that we saw earlier. And they essentially don't run ROS on the quad rotor. That's just got a PIC on it with an XD, just like how most of our systems do. And they've got a motion capture system that's tracking where that thing is. It's got little balls glued on it, and they're tracking it in real time. And ROS is getting that motion capture data, doing all the control calculations, looking at the robot's pose and deciding what the control signals should be sent to the robot, and then it's sending them out. So they're doing all the coordination of all this data coming in from ROS, but the robot itself is just a PIC. I mean, the system that Jake and I are developing is sort of going to work that way. I would imagine, like, if Andy were to use it, it would be that way. Nelson, if you were to use it, it would sort of be that way. The Swarm team, same thing. And this guy, this bottom bullet is almost the most important. I kind of said it earlier, but all of the control algorithm development is done totally in simulation. You don't have to write any new code to switch between having the actual robot flying around and just simulation. Because the way ROS passes the messages is the exact same. So if you write a control robot node and a simulation node that both subscribe to the same message, starting one versus the other is very easy. Really makes it nice for development. So just in case, has anyone not seen this video? This video. It's awesome.
It flies through the hula hoop?
Yeah, it flies through hoops. It does flips.
Show it.
Yeah. Show it.
Okay.
Yeah.
Just a little short on
This
time.
video presents autonomous control capabilities for a quadrant helicopter. We use a 20-camera Vicon system and an onboard IMU for state estimation. Here we show single, double, and triple flips. We developed a method for flying to any position in space with any reasonable velocity or pitching. We use the method to fly through windows at various angles. Here there's less than 3 inches of clearance on all sides of the quadrilateral. We also fly between other quadrilaters. The same method can be used to descend or ascend through a horizontal slot. By placing Velcro on the bottom of the quadrilateral and on a target, the quadrilateral can perch on a surface. Here we demonstrate perching on an inclined surface. And now on an inverted surface.